Hello to everybody at the Cosmology at Home conference, and also anyone who stumbled across this on YouTube. Today we are going to tell you about the cosmological constraints from the 4th data release of the KiloDegree Survey. My name is Heymans.
And I'm Tilman Troester.
And together we're going to try and take you through these new results. Now, the analysis that we're showing you today is just one of 3 talks that are happening at the Cosmology at Home conference. So we recommend you also go and look at the talks from Benjamin Yakimi. He's going to give you a guide to precision cosmology with galaxy surveys. And also Angus Wright, who's going to tell you about how to calibrate photometric redshifts for weak lensing studies. And Tilman and I are going to try and take you through the other 3 papers that support the cosmology results we're showing you today. We'll take you through how we actually make these measurements very briefly, the cosmology constraints from our cosmic shear analysis, and also something that we're calling a 3 times 2-point analysis, which will become clear if you haven't heard this terminology already. Okay, so what is KIDS? So the KiloDegree Survey is an ESO public survey. We are now at our 4th data release that's spanning more than 1,000 square degrees. That's why we're calling this KIDS 1000. The image that you can see here, what we've done is we've projected our large scale structure maps up onto the sky, so you can get a sense of just how much of the extragalactic sky we've surveyed now. KIDS is imaging in 9 bands from the optical all the way through to the near infrared. It was designed for weak lensing, so it takes the absolute best weather conditions on Paranal in order to assemble this survey. But contrary to what this picture would suggest, these 2 stripes are not on the same part of the sky. And so you can see this here on the full sky map. Here's KIDS north is our equatorial region, and KIDS south down here. Now we overlap with 2 spectroscopic surveys. This is the BOSS survey in the north here, that's a spectroscopic survey of luminous red galaxies, and 2DF Lens, which is a survey to mimic BOSS in areas where we have accurate lensing data. And that allows what we call same sky survey science. The cosmological constraints we're going to show you today are coming from 3 different probes of the large-scale structure that really benefits from this optimal survey design of having overlapping photometric and spectroscopic surveys. The first probe is called Cosmic Shear. That's looking at how background galaxies appear to align with each other. Now what's happening, you can see in this cartoon, we've got light from these distant galaxies. It's being lensed and distorted by the foreground large-scale structure. So galaxies that are close to each other on the sky appear to be lined up with each other. They appear to be lined up with each other because they've both been lensed by the same foreground structure. Now we can also look at how the galaxies are clustering within that large-scale structure. And we can also look at how the galaxies in the foreground are lensing the background KIDS galaxies. So these are the 3 different 2-point statistics that we're combining together: cosmic shear, galaxy clustering, and galaxy-galaxy lensing. And the combination of these 3 different probes allows us to break degeneracies that exist when you look at these probes individually. So it's a very powerful combination of large-scale structure probes. Now, we're going to focus at the start on the cosmic shear analysis. To do this, we need to measure the shapes of the galaxies and their 3D position, both RN deck on the sky and their photometric redshift. See Angus Wright's talk for how we get accurate photometric redshifts, but once we've got them, we split our galaxies up into 5 different redshift bins, and then we can look at how the large-scale structure is evolving as a function of time in the universe. Let's talk about those shapes though. So when you measure the shapes of the galaxies on the sky, most of the signal that you can get is just coming from the atmosphere and the telescope. So one really nice thing about KIDS, because we have this near infrared data, we've got a really clean way that we can separate the stars from the galaxies. Now the stars tell us about the point spread function, everything that's happened to the light since it's hit the atmosphere. And the galaxies, we can then invert all of these terrestrial distortions in order to recover the pure cosmological signal from those galaxies. Now, there's a paper by Ben Giblin where he takes through a load of different null tests that we've done to ensure that the shear measurements that we've made are really robust. And if you are interested in that, I encourage you to go to the 1-hour seminar on cosmology talks. You can see the YouTube link at the top here, where Ben has taken you through all of those different null tests at a slow pace. But one of them is just here for you to have a look at. Each of these different panels are different combinations of different tomographic bins. So, for example, the panel called 5.5, this is looking at the B modes in the correlations between the galaxies in our 5th tomographic bin. Lensing will only give you E mode distortion. Sorry. If you see any significant B mode distortion, it means that there's something else there in your data that's not cosmological. Highly correlated data points don't do chi by eye. That's why we've given you these p-values here, so you can assess for each bin whether the B mode we're measuring is consistent with pure noise, and it is in every single bin and indeed for the data set as a whole. Our PSF model is shown to be very accurate. We've identified some instrumental defects that are very interesting. If you're interested in readout electronics, I started astronomy because I wanted to understand dark matter and dark energy, and I now know about CCD effects in readout electronics. But all of those defects we found very low in comparison to our statistical noise, so that's good. And there's a shear ratio test where we look at the robustness of both the shear and the photometric redshifts together. We're happy that our catalogues are very robust, that we understand the level of systematic in them and that it is insignificant in comparison to the statistical noise. And so that allows us to move on with our cosmological parameter estimates. This is our cosmic shear analysis, so that's the correlations of galaxies introduced by the large-scale structure. Lots of data here. These are the B modes over here, so we can ignore that. And here we've got our E modes. Up here, this is our 5th tomographic bin correlated with itself, so you get a strong signal, and that's because the light from those galaxies has gone through a large amount of the large-scale structure. And as you go down here to our low redshift galaxies, you see there's no signal at all, and that's because there's very little large-scale structure there to do in lensing. The pink lines that you can see here, that is our theoretical model. It's the flat lambda CDM model, fixed neutrino mass. We include intrinsic galaxy alignments, baryon feedback, how that impacts our nonlinear matter power spectrum, and our analysis includes the uncertainty on our photometric redshift calibration and shear measurement calibration. Now, those of you who have known me a while will know that for my entire career, we have been finding results, cosmological constraints that are slightly inconsistent with the constraints from Planck. So this dates back right to the first big weak lensing survey, CFHT lens in 2013. So this is where we were with kids on July 9th, which was the day that we unblinded. The way we blind our analysis is we create 3 versions of the catalogue. One is the truth, and the other 2 have been modified in some way such that when we do our cosmological parameter inference, which you can see here in these big different pink bananas, that they are offset by at least 2 sigma. We never know whether the truth is in the middle, at the top, or at the bottom, but we all have our own unconscious or conscious biases about what we actually want it to be. Now, this time I really wanted to agree with Planck, because Planck has exquisite measurements of the cosmic microwave background, and the lambda CDM model fits it absolutely perfectly. The lambda CDM model also fits our data very well, but just with different values for this particular parameter here, S8, which is a combination of sigma 8 and omega m. So we had these 3 different results. We didn't know which one was the truth. You might be interested in a poll that we took at the unblinding party. Here, which blind would you like to be the truth? The majority of our team wanted a 4 sigma tension with Planck. So we could really make a media splash. And which one did we think was the truth? Well, most of us thought there would be some tension with Planck, since we'd found that with our previous data analyses. And the result, which Tilman's going to take you through in a bit more detail about exactly how we quantify that tension, it's roughly a 3 sigma tension with Planck that we're finding. So this is the final result for the cosmic shear measurement, so there's no blinding in here. This is the actual result, and the different colors that you can see here are just different statistics that we've used to extract that cosmic shear information from the data, and these range from real space through to Fourier space statistics. Now, what this means, having a difference between these results, means that that flat lambda CDM model that we're using to infer our two measurements is kind of inconsistent with each other. And it's interesting that Planck is measuring this at high redshift and we're measuring something at low redshift. So there could be something strange going on there. Here are just some sensitivity tests. At the top here, you can see our constraints for our three different statistics. They're very consistent with each other. These are all the choices that we can make, different ways of deciding how we're going to marginalize our uncertainty on the calibration, corrections to the shear and the photometric redshifts, our baryon or intrinsic alignment models. We can see we're very insensitive to those choices. At the bottom here, we're removing different photometric redshift bins to see how our results are dependent on that choice. And you can see here that if we remove redshift bins 1, 2, or 3, we get very little difference. And that's just because there's essentially very little cosmological information in those low redshift bins. You see more of a difference between whether we remove bin 4 or bin 5 here. And that makes more sense if you think about essentially all of our information is in bin 4 and bin 5. And so if we throw out 1, we're losing about half of our information. So we expect those results to change by about 1 sigma, which is what we see here. But that's a very hand-wavy discussion there. And so I'd encourage you to look at Marika Asghari's paper, where we do a full Bayesian internal consistency analysis. That demonstrates that the difference that you see here between bin 4 and 5 is perfectly expected from just statistical fluctuations when we're removing parts of our data set. Interestingly, though, that analysis does highlight bin 2 as an outlier. We don't understand that yet. It could be that we haven't quite got the redshift distribution right for that redshift bin. But as you can see here, the removal of that bin, which our internal consistency tests flag as a potential problem, doesn't change our results at all. We're completely insensitive to that. So more work needed there, but it doesn't change any of our conclusions that we're going to show you today. I've been very remiss and I haven't compared our results at all yet to our academic cousins, the Dark Energy Survey and the Hyper Supreme Camera Survey. So you can see a compilation of results here. Now this is constraints on this joint parameter S8. These are all cosmic shear only results. And you can see here good agreement between the different statistics we're analysing with KIDS 1000, and also very good agreement with the constraints from the Dark Energy Survey and the Hyper Supreme Camera Survey. But all three surveys that are independent teams, independent telescopes, independent cameras, they are all on the low side in comparison to Planck. Okay, I'm going to hand over to Tilman now, where he's going to show how we build this up now by adding in those 2 additional probes of the large scale structure.
Thank you, Catherine. So Catherine showed us what happens to light as it passes through the large-scale structure, but of course there's other traces that also trace the same underlying matter field, the galaxies. So for the cosmic shear part of our combined analysis, we used the band power measurements, which are particular kind of two-point correlation function that is better suited to excise physical scales that we don't believe we can model accurately, like small scales affected by AGN feedback, for example. Now for the galaxy clustering, we use BOSS DR12 galaxies, so we use a spectroscopic sample. Specifically, we measured the anisotropic correlation function in 2 redshift bins. These are shown here. And then we further split up the correlation functions with respect to the angle of the line of sight in correlation function wedges, and then do a full shape analysis of this measurement. So this very closely follows the BOSS DR12 analysis of Sanchez et al. What you see here is our measurement. We caution against doing a chi by eye because our measurements are very strongly correlated. Now going on to the combination of the galaxies and the lensing, we have a so-called galaxy-galaxy lensing. Here we use the same galaxies that we use for the clustering for the lenses. So this is shown, the redshift distribution of those are shown on the top left here. And on top of that, we add the lenses from 2DF lens for the southern patch of our KID survey. For the sources, so the galaxies is our lens, but it's foreground galaxies, we use the same galaxies that we use for the cosmic shear. The redshift distributions are shown here at the bottom, and our data vectors shown on the right. We see that they're sort of gray on this plot on the right, and these are the data points that we do not use in our analysis. The reason for that is that our modeling of the bias of the galaxies is the same that we use for the clustering, and it's a predictive modeling. So we can't really push that to the small scales that we would like to for lensing. So even though we have all these great measurements, at the moment we don't have the modeling that is accurate to the scales that we need to analyze this data vector in full. But just taking what we have and then pulling that through to a parameter inference is the results we get. So in pink, we have again the cosmic shear only results. So these are the same results that Catherine showed before. If we, on top of that, add the galaxy-galaxy lensing, we go to the dark purple. Now, because we have to cut all these small scales that have all the lensing information in galaxy-galaxy lensing, adding galaxy-galaxy lensing doesn't actually increase our constraints by much. What we can do to increase our constraints, however, is adding the galaxy clustering. So that mainly helps to constrain omega m, so how much matter is in the universe, and really cuts through a degeneracy between S8 and omega m. And combining all of that together, we end up at the red contours, which is our main results. It's the KIDS 1000 3x 2-point joint analysis. Now you might ask, how far is the red contour away from the gray contour, which is the Planck CMB result? And if you just to care about S8, which is the parameter we set out to measure, then that tension is 3.1 sigma. And it's quite stable across various different tension metrics that you can come up with. Now, if you say, well, S8 isn't the only parameter that we're measuring. What is the difference in the distribution between Planck and our results if we take into account all the shared parameters? And over that high dimensional parameter space, the tension goes down to about 2 sigma. It just reflects that we have good agreement in omega m, for example, H is in reasonable agreement, and so on. So depending on the questions you're asking, we're still left with a tension of like 2 to 3 sigma. And it will be very exciting to see what DES and HSC find and where this goes in the future. Instead, I'll hand it back to Kerstin for the conclusion.
Classic Zoom error. That shows that we're recording this live. In summary, these are our results. We have a constraint on S8 that is now as precise as the constraints that you get from Planck, but as Tilman said, it's about 3 sigma in tension. So your one sentence summary is that the universe is less clumpy than Planck predicts. This sort of final figure that we're showing here is looking at things in terms of sigma 8 and omega m again, and you can see that that tension that we're finding is driven by sigma 8. So it really is the clustering of the matter which we're finding in tension with Planck rather than the total amount of matter. I hope we've given you a bit of a flavour of how this result is validated. We've got a bunch of different mock surveys, image simulations, null tests. Angus is going to take you through the spectroscopic photometric clustering analyses, and all of the systematic uncertainties we've identified has been folded through as nuisance parameters. So an interesting result, tantalisingly close. It's not the 4 sigma that a lot of us wanted on the day of unblinding. So we could really say that there really is something significant here. It could be we've just looked at an unusual patch of the universe in the 1,000 square degrees that we've surveyed with kids. So as Tilman said, very much looking forward to seeing the latest results from the Dark Energy Survey and the Hyper Supreme Camera Survey when they come out. Because if they continue finding low results, as we are finding, then it's a real indication that there's something missing from that flat lambda CDM model that otherwise provides really excellent description of all of our observations. So we will leave it there with a thanks to all of the KIDS Consortium Here are some of them in happy days pre-lockdown, but we're doing quite well through Zoom as well. We'd also like to thank our funders, the European Research Council in particular, and we are very much looking forward to your questions when the discussion session opens at the Cosmology at Home conference. So we will say farewell for now.